What if there were devices that could solve problems quickly and easily? Problems that would require even the quickest supercomputers billions of years to solve. What if we had computers so powerful that they could simulate all of nature's processes and provide us with answers to the major questions of humanity, from the creation of the universe to the evolution of life? Well, after that, we would have reached the exciting world of quantum computing. Indeed, scientists at the famous University of Oxford have now achieved a significant turning point in this field, connecting two quantum computers for the first time to solve a highly complex quantum task together. In the course of this, a quantum logic gate was teleported over a distance of 2 meters. But how does something like this actually work? Why are quantum computers suspected of radically changing our daily lives in the future? And what actually gives them their unparalleled computing power? A report that makes you sit up and take notice. A few weeks ago, the leaders of Google Quantum AI announced that Willow, a quantum processor, completed a task in just 5 minutes that would take the world's best supercomputer, believe it or not, 10 quadrillion years. That's a 1 followed by 25 zeros. But how is it that quantum computers turn even the most powerful computers of our time into lame snails? To understand this, we first have to visualize how our current everyday devices work. Whether you're watching this video on your laptop, your cell phone, or your tablet, all these devices work with bits, units of information that can assume either the state of 1 or 0. In the computers of today, these states are represented by electricity in the processor. Electricity on means 1, and electricity off means 0. As their name suggests, quantum computers, on the other hand, use quantum bits, or qubits for short. These can also assume the state of 1 or 0, but they have another remarkable ability that clearly distinguishes them from classical bits. Additionally, a qubit can reside in both state 1 and 0 simultaneously, or theoretically, in an infinite number of states in between. If we imagine a classic bit as a coin that either shows heads or tails, a qubit is a coin thrown into the air, spinning rapidly. As a result, we cannot say which side is currently facing up because it is in both states simultaneously. Ultimately, it is precisely this property of the qubit that makes a quantum computer many times more efficient than a conventional computer. It needs significantly fewer qubits than bits for the same calculation. In a conventional computer, 2 bits can only represent one number at a time, but as previously stated, a qubit can assume an infinite number of different states simultaneously. Even if we assume just 2 different states at the same time, each additional qubit doubles the number of simultaneously representable states. While 3 qubits can already assume 8 states simultaneously, 300 qubits can represent as many as 2 to the power of 300 states, a number greater than the number of particles in the universe. But that is not all. In addition, the qubits in a quantum computer can also be quantum entangled. This means that they are coupled in common terms. As soon as a qubit is brought into a certain state, the state of its partner becomes entangled at that exact moment. And, mind you, at faster than light speed. This provides the context for the fact that calculations in a quantum computer can also be carried out faster than the speed of light. What does this achieve? Or, to put it another way, what practical uses do these wondrous devices actually have? Well, none at the moment. But as soon as the state of the art allows, scientists want to use supercomputing power to simulate the interactions of molecules or their possible states, thus achieving new breakthroughs in the field of drug development. AI could also take a giant leap forward with the help of quantum computers. The development of new materials and the fight against climate change could also benefit from the power of this futuristic technology. For now, we simply cannot foresee exactly how many applications quantum computing will have. Even experts believe that we will use these computers to simulate all of nature's processes, finally crack the great secrets of the universe, and answer the question of the origin of life. The challenges of qubits. However, qubits present challenges for researchers. All this, mind you, is only attainable with the assistance of exotic computing and information units. But how is a quantum bit created in the first place? Experts have various options at their disposal to generate qubits. Google, for example, uses special quantum chips on which weak currents flow in circles in the smallest of spaces. An individual circulation current is equivalent to a qubit. Ions can also be brought into different states and read with the assistance of microwave radiation. The aforementioned Willow quantum processor, for example, is equipped with 105 superconducting qubits. Aside from that, it is also possible to create qubits by trapping ions in magnetic and electric fields. Once trapped in an ion trap, they can be brought into different states using microwave radiation and thus loaded with information. At least, that's the theory. The practical truth is that the field of quantum computing still faces some significant problems. After all, there's a reason why we're not all walking around with a quantum smartphone in our pocket. To manipulate and capture the moving particles of the qubits, they have to be immobilized by cooling them almost to absolute zero, 273.15 degrees Celsius. Furthermore, qubits are extremely sensitive, and any disturbance, no matter how small, destroys their quantum state. Regardless of how well experts protect them from sound, magnetic and electric fields, and all other external influences, at the end of the day, qubits only remain stable for fractions of a second. Overcoming the scaling problem. Corresponding calculations must, therefore, be completed in this extremely brief amount of time. To achieve this, researchers must constantly increase the number of qubits working together. But this is easier said than done. Although quantum computers with 1,000 qubits made of ions or superconducting quantum dots already exist, researchers suspect that the quantum computers of the future will need millions of qubits to be truly practical. The more qubits a quantum computer has, the more unstable and error-prone it becomes. Experts have to resort to complex correction methods. In the case of Willow, for example, scientists implemented a so-called surface code. This means that quantum information is no longer stored in a single qubit, but is distributed across several physical qubits. Together, these form a logical qubit, a computing unit. In this manner, the required information is preserved even if a single physical qubit makes a mistake. But perhaps, and this is the exciting part, this scaling problem can also be avoided with the assistance of teleportation. How Oxford scientists teleported a quantum operation. It should be noted that quantum teleportation differs somewhat from the wondrous technologies presented in Star Trek and the like. While teleportation in science fiction refers to machines that transport matter from one location to another at the push of a button, quantum teleportation merely describes the transfer of quantum information, such as the spin state of an atom, to a distant second atom. Now that this is clear, we can move on to the enthralling work of the Oxford scientists. They used modular quantum computers, with each module containing only a relatively small number of qubits. These modules were connected to each other via classical and quantum channels. The individual quantum modules remained relatively steady, so they could perform more complex quantum algorithms in combination. The Oxford researchers successfully connected separate quantum processors into a single, fully connected quantum computer. This breakthrough lays the groundwork for larger, more powerful quantum computers and the future quantum internet.